Renowned astrophysicist Neil deGrasse Tyson is the first Frederick P. Rose Director of the Hayden Planetarium at the American Museum of Natural History. After receiving his BA in physics from Harvard University and his PhD in astrophysics from Columbia University, Tyson received 14 honorary doctorates and the NASA Distinguished Public Service Medal. From 1994 to 2003, he served as a visiting research scientist and lecturer in the Department of Astrophysical Sciences at Princeton University. Dr. Tyson has written 10 books, including Space Chronicles, Facing the Ultimate Frontier. His contributions have been recognized by the International Astronomical Union in its official naming of asteroid 13123 Tyson.
You know, of all the amazing things about the universe, I think two stand above all the rest. One of them is that we know so much about the universe, but another is that there's even more that we don't know. And what I want to focus on for this lecture is the inexplicable universe from a time gone by that is now explained. Human cultures have for a long time harbored scientific mysteries. In fact, in the pre-scientific era, that would be before Galileo, 400 years ago, before then, many of nature's most unknown mysteries were thought to be the work of divinity. Take, for example, epilepsy. There's someone writhing on the ground, your best friend, frothing at the mouth. If you're driven by Christian theology, your first thought is, the person is possessed by the devil. That's the natural explanation for what's going on there, in the absence of any other knowledge about neurosynaptic processes. In another example, you could go out to the woods one morning, one damp, cool morning, and you'll find this circle of mushrooms. No one knew how they got there. You were there the day before, there was no trace of mushrooms. And now, there's a perfect circle of them. These were known as fairy circles. And people imagined sort of woodland nymphs, woodland fairies coming to have a jamboree, and these were their chairs. Little fairies, of course. These were their chairs, where they celebrated whatever were their rituals of the night. We would later learn that, of course, mushrooms they're not solo organic entities. They're, in fact, one spore can generate many, many mushrooms. And if a spore drops in one spot, it can work its way out and get ready for just when the conditions are right, just the right temperature, just the right humidity. And then they all pop up, equidistant from where that spore first dropped. So explanations came later to these phenomena. And of course, we know epilepsy is the result of random firing of the brain, uncontrolled firing, that leaves you helpless in the presence of a brain gone awry. So what we found is that things started to change in the rise of the experiment. If you go back in time to Aristotle's day, people imagined that you could just sit in a chair and just think about the universe. Didn't have to go out and test it. You just thought it up. Aristotle imagined that heavy things fell faster than light things. Of course, yes, a rock falls faster than a feather. The feather feels the air resistance on its way down. But take a heavy rock and a light rock, they'll actually fall together at the same rate. Aristotle, however, said that the heavy one will fall faster than the light one in direct proportion to its weight. This is patently false. And it would take Galileo 1,500 years later to demonstrate that this was the case. He describes the experiment of dropping two balls from the side of the Leaning Tower of Pisa. And they're both falling at exactly the same rate, hitting the ground at the same time. Of course, that would happen with a rock and a feather. You just have to evacuate the air from where you're doing the experiment. In fact, that was indeed done, that very experiment, on the surface of the moon. So what I want to do for this lecture is focus on several stunning examples of profound mysteries that plagued the deepest thinkers of their day, but ultimately got explained. There was a single biggest scientific mystery of the 19th century. It preoccupied the greatest minds of that period, and what it related to was at the core of our understanding of space itself. What's behind it? Well, we know that waves require some kind of material medium through which to travel. And the best and most common example of a wave is sound. Sound moves through air, but if you take away the air, it cannot propagate. You may have remembered this experiment. It might have happened in your high school science class. You have a ringing bell, and you enclose that bell in a glass container, and you start pumping the air out of that glass container, and the ringing bell gets dimmer and dimmer and dimmer to hear. And at some point, you don't hear it at all, yet you still see it clanging away. That's evidence that sound cannot pass through the vacuum that you just created. Well, if light is a wave, then it too must require some kind of medium through which to travel. Here's the problem. Empty space is a vacuum, and we know that light reaches us from empty space. The moon is in space, the sun is in space, the stars are out in space, and there's a vacuum between us. So it was hypothesized that no, there's not air out there. There's got to be something, some substance, some medium that light requires for it to propagate. And we gave it a name. My science ancestors of that period, we gave it a name. It was called the ether. The ether. We ought to be able to measure it. Two scientists came along. This is in the late 1800s. The physicist Albert Michelson and the chemist Edward Morley, two American scientists. And they got together, collaborated, and perfected a new kind of tool called the interferometer. It's a special instrument that allows you to measure with high precision distances and speeds. And so in 1897, they conducted what came to be known as the Michelson-Morley experiment. So here's what they did. They said, all right, here's Earth. I'm going to measure the speed of light with the movement of Earth around the sun. Then I'm going to measure the speed of light against the movement of Earth around the sun. And if there is an ether out there, I ought to be able to show that the light added to Earth's movement, and I measure the speed of that, I'll get the speed of light plus the speed of the Earth. And coming back the other way, if I make that measurement, I'll get the speed of light minus the speed of the Earth. That makes complete sense. Of course it does. If you're riding in a train, back then it would have been a train, not a car. You're riding in a train that's going 30 miles an hour and you send something forward 10 miles an hour, you add them, that object is moving 30 plus 10, 40 miles an hour relative to the ground. Come back the other way and you throw it out the back end of the train, that speed will be 30 minus 10, 20 miles an hour relative to the ground. It's that simple. That's all they were trying to do with the speed of light. Upon conducting this experiment, what they found is that the speed of light was the same no matter where they made the measurement. And this was astonishing. It was the greatest null result ever found for a scientific experiment. A null result is you expect to find some kind of measurement and you don't. Usually those experiments are like not interesting, but this was the most interesting null experiment ever conducted. And so what do? Everyone knew there had to be an ether. So there were a couple of guys who said, all right, we can solve this. There's a fellow named Lorentz and another one named Fitzgerald. And they got together and said, we know what's going on because there's got to be an ether. your measuring tools have contracted in the direction of motion. They've physically contracted to fool you into thinking that you're getting the same speed of light. That must be going on. Now, just think about that. So embedded were they in the existence of the ether. The ether, this traditional concept that a wave requires a medium, that they would not even entertain the possibility that there was no such thing as an ether. They would rather assert that something odd was happening to your measuring devices. They were trying to rescue the hypothesis of the stationary ether. Now, we happen to know that physical materials can't just physically contract. That's not how they behave. They never behave that way. What we would later learn, not just a few years later, is that light, in fact, does not need a medium after all through which to propagate. It is a self-driven wave, a combination of an electrical wave and a magnetic wave. It was an astonishing revelation of the day. No ether. And what state of mind, though, allows us to recognize that the speed of light remains constant? Albert Einstein to the rescue. 1905, special theory of relativity. What he noticed was that those equations that would shrink your physical objects that are doing the measurements to conspire to give you the same speed of light, what Einstein showed is, no, they don't actually shrink. What happens is the speed of light is actually constant. It's actually constant. And what's going on is that the rules of special relativity change how you end up making that measurement while you're doing it. And when that comes about, you find that the ether is not necessary, the speed of light is constant, and we have walked through a proscenium in the history of science where the ether was the last grasp, the last bastion of classical physics before the 20th century would open its doors. Because in the 20th century, what we came to learn is that whatever was your common sense that you were invoking about how the world must be, 20th century science and onward entered a time where, in fact, in order to understand the universe, at least some of the time, you had to abandon your senses. Next up is the discovery of the planet Neptune. But first, let's go back in time to 1781 for the discovery of the planet Uranus by Sir William Herschel. He's the only one in town with the big telescopes during that day. And he found Uranus by accident, actually. He thought he had found a comet. Nothing else would have moved against the background stars except comets. It was inconceivable to him that he could have discovered a planet because nobody had ever discovered a planet before. Mercury, Venus, Mars, Jupiter, and Saturn in the sky are visible to anyone who looks up. They don't require a telescope. He was in denial for so long. He thought he had seen a comet, and he would say things like, "Curious comet this is. It refuses to show any fuzz, as any good comet ought to." Fact is, the man discovered Uranus. So here's the question. Does Newton's law of gravity apply that far out in the solar system? Newton's laws of gravity had been tested between the Earth and the Moon and all the inner planets and the sun, and it was working. It was good. It was powerful. It was predictive. And so here we are at the outer reaches of the solar system. Well, let's test that. We're in the era of testing ideas. So let's wait 70 years. And over those 70 years, we're going to get data on where Uranus is in its orbit. Okay? How long does it take Uranus to complete an orbit? 84 years. So 70 years is most of 84. So you're doing good. You've got a lot of good data to compare. You say, where should Uranus be according to Newton's laws? And where do I measure it to be in the solar system? Is there a difference or not? If it's bang on, we're good. Newton's laws work out there, we're fine. What we found is that they didn't match. Do we throw out Newton's laws? They're pretty good. They're working for us. No one really wanted to abandon them. If you don't abandon them, what are your options? Maybe there's another source of gravity you haven't reconciled with your efforts. All the other sources of gravity you factored in, you're missing one. And if you included it, maybe that would account for why it looks like Uranus is behaving badly. So, thus began the hunt. British mathematician and astronomer John Couch Adams, he was a specialist in celestial mechanics. This is the physics and the mathematics of the movement of bodies in the solar system. And a French mathematician, Urbain Jean-Joseph Leverrier, did exactly the same thing. And it's a tricky problem because typically you would use Newton's laws by saying, here's a body and here's a body, calculate the force between them. This is different. Here we have the force between them, but there's some body out there and we don't know where it is or how much mass it has. So it's an inversion problem with Newton's laws. You have to calculate things backwards from what you're accustomed to, and that takes pages and pages of data and calculations to get it right. So each of these brilliant mathematicians predict where and when you should find the perturbing object that was out there. It happened to be Leverrier, who was friends with Johann Gottfried Galle in the Berlin Observatory. He was an astronomer there. Leverrier assisted him, told him, here's where you should look, and here's when you should look. Johann Galle looked where and when Leverrier said he should find it. Within 1 degree of the predicted position, he found a new planet. The planet to be known as Neptune. This was a triumph of mathematics and the laws of physics. It was a case where you weren't using the past history of rhythms to predict the next event. You do that with like the phases of the moon and eclipses and things where you have a good record of what it was doing before. This was a case where there was no previous record. A planet was predicted and discovered simply by laws of physics and understanding the operations of nature. This would shape the expectations of all subsequent discoveries in the solar system because Newton's laws were working. And next, we would apply those very same laws to the orbit of Mercury. Nature can be subtle. I don't know if that's a good thing or a bad thing just yet, but it's certainly true. I'll give you some examples. Take Newton's laws. Newton's laws of motion and gravity are powerful tools that enable us to understand and decode the movement of objects in the solar system. And it's worked in every place we'd ever applied it. So why not be cocky about it and say it'll work even in places we have yet to imagine? These methods and tools are empowering our capacity to understand objects in the solar system. Okay, I'm with you on that. That Newton's laws, they're good. They're good. But let's see what happened. Over the centuries, careful timing of the movement of Mercury around the sun, that's the innermost planet. It orbits in an ellipse. It turns out the ellipse precesses around the sun. We've known this. This is not news, right? While Mercury is orbiting, the entire ellipse precesses ever so slightly. All right, we're fine. Turns out, when you calculate how quickly this should precess, and then you observe how fast it's precessing, those two numbers do not match. They differ from each other by, if you're angle fluent, 43 arc seconds per century. That's small, and it took a long time to establish that baseline of measurement to say that these two do not agree. All right, well, what's causing it? Nobody knew. But In 1859, riding high on his successes with the planet Neptune, Leverrier said, I got this. Look, I've been there before. How do you think I've helped you find Neptune out there? There must be some other source of gravity we've yet to tally in our inventory of objects in the inner solar system. So he said, I got it. Maybe there's a belt of asteroids, a second asteroid belt in the solar system between Mercury and the Sun. And the collective gravity, that's what's giving an extra tug on Mercury. Within a few years of that, there was an astronomer who made a measurement of a planet moving across the Sun's surface, a planet that was not Mercury. Leverrier said, okay, I don't need the asteroid belt. It must be that object. In fact, I'll name it. I'll call it Vulcan. Awesome name for a planet. Anything that close to the Sun, that's the name it has to have. That's the root of the word volcano. So that became the scapegoat for this extra tugging on Mercury to create that difference in the precession. Problem is, another person with a better telescope observing the Sun at the same time as this other astronomer was making his measurements said, I saw nothing go across the Sun. There must be something wrong with your measurements. And practically overnight, Vulcan disappeared from the data. It was a faulty measurement that had been reported. So now Leverrier was left with nothing to credit for the movement of Mercury. But maybe you can still get away with it. Maybe it's so close to the Sun, it's always lost in the glare. Plenty of people were happy with that explanation. And we went on saying, yep, it's Vulcan. Never found it, we don't know where it is, but surely it's there. Enter Albert Einstein. 1916, he publishes the general theory of relativity, the modern theory of gravity. In it, space and time is a fabric. Think of it as a deformable fabric. And gravity is not a force between two objects. Gravity is the shape of that fabric. And bodies move according to where that shape tells you to go. And when you factor in all the tenets of relativity, what we found is that Mercury was following the severely curved fabric of space and time in the vicinity of the extremely significant and strong source of gravity that is the Sun. In fact, Newton's laws do fail when you're that close to an extreme source of gravity. This shocked the world. And it's a reminder that here we were invoking Newton's laws. We were ready. We invoked Newton's laws to discover the planet Uranus. And in our cocky ways, we said, we're going to fix the Mercury problem the same way, only to find out, no. Mercury required an entire new branch of physics to be invented, just to explain it. And so, yes, nature can be subtle. That is the beauty and the challenge that the modern scientist faces. You know, not all investigations of the universe involve pieces of the unknown. Occasionally, people are challenged to take it all in and come up with a coherent, complete understanding of the known universe. In fact, the people who get to do this are part of cultures that value deep thought, that actually have the luxury of time to invest in trying to deduce the nature of the known world. One of my favorite examples of this is Claudius Ptolemy. He was an Alexandrian astronomer and mathematician, and he was around at 2nd century AD. He came up with a coherent, complete understanding of the known universe. And he put it all in a book called Almagest. Almagest is actually Arabic for the greatest. Aptly named, I think. Now, his ideas happen to be wrong. He put the Earth in the middle of the known universe. That's the geocentric model of the cosmos. But when you think about it, that's what the world looks like. Everything orbits Earth. And does it feel like Earth is moving under your feet? No. So his model was what made common sense to everybody. But deep down inside, I think he was still didn't feel like he grasped it all. Because he would follow the movements of the planets in the night sky. They would slow down, stop, and then reverse, call it retrograde. This is complicated motion to try to explain. In his greatest work, he penned in the margin my favorite quote of all time. He said, "When I trace at my pleasure the windings to and fro of the heavenly bodies, I no longer touch earth with my feet. I stand in the presence of Zeus himself and take my fill of ambrosia." That's Claudius Ptolemy basking in what he understood about the universe, but was humble in his ignorance. Because deep in that quote was the recognition that I don't think he really believed he fully understood what was going on. Why else would he bask in the presence of Zeus? Well, it would be 1,400 years where people just accepted the geocentric model. Again, that's an era where experiments on ideas is not yet an understood thing to do. 1,400 years would go by. Nicholas Copernicus, 1543, on his deathbed, would propose the heliocentric model of the universe. He wasn't content with what the hoops Ptolemy had to jump through to account for what we saw. How else do you get planets to go forward and backwards and forward and backwards? Ptolemy had systems of multiple orbits on top of orbits called epicycles. Things orbiting nothing in space. In fact, the word orbit wasn't even quite defined back then. This was just movements. And Copernicus said there might be an easier way. Let's put the sun in the middle of the known universe, and if you do that, Earth becomes one of the planets. That's heretical. Copernicus waited to his deathbed before he published this, knowing the kind of retribution that would be exacted upon him in that period of Europe, the mid-16th century. Did not take kindly to heretics. So you can't kill him, he's already dead. So he puts out the heliocentric universe on his deathbed. It was right in every fundamental way, except he had the orbits as perfect circles. It would take a few years to iron that out. But what's important here is that the world embraced an idea that was wrong, but made sense. Wrong, but it made sense. That ought to tell us something. That not everything in the world that makes sense is correct. And if that's the case, then who are you? What of Ptolemy's Zeus? What of the reverence he's showing? If he actually understood it all, would Zeus have even shown up in his quote? And if you're prone to assert that God is the influence of all that we don't understand, because the hand of God is greater than anything your mind can comprehend, then what of God? Throughout history, the urge has been strong to, upon recognizing your area of ignorance in the universe, to assign the handiwork of God to those ideas, to those phenomena. If you feel that way about prevailing ignorance, then you're actually in pretty good company. Isaac Newton did just that in his most famous work, Principia Mathematica. The translation from the Latin is The Mathematical Principles of Natural Philosophy. That's the full-up title of that book, published in 1687, in which he discovered the laws of motion, the universal law of gravitation, and in it, it represents the fruits of his effort for having discovered calculus to solve some of the problems that he engaged in. All right, so in this great work, he tries to understand the solar system as a total collection of objects. And he applies his universal law of gravitation. It calculates two bodies at a time, Earth and the Sun, Earth and the Moon, Earth and Mars. When you do this, the calculations come out just fine. But of course, the solar system is the sum of all the tugs that go on with all the planets. His attempt to do that with his two-body equations failed. What did his calculations show? That these multiple tugs on all the planets by all the other planets would render the solar system unstable and planets would fly out into interstellar space. Well, first of all, he knew that that wasn't happening and that his universal law of gravitation worked. So he concluded that divine providence must be at work. The hand of God is stepping in every now and then to correct things. Okay, well, a century would pass before the publication of a great work of mathematical physics by the French mathematician Pierre-Simon Marquis de Laplace. He came out with a 5-volume tome called Céleste Mécanique, Celestial Mechanics. This is at the turn of the century from the 1700s to the 1800s. A contemporary of Napoleon, by the way, but I'll get back to that in a moment. So, in this volume, he develops a new branch of mathematics that allows you to take one major source of gravity and a lot of other little sources of gravity. It's called perturbation theory. It is the exact kind of math necessary to calculate what the entire solar system is doing all at once. When he does this, he shows that the solar system is stable, contrary to what Isaac Newton attempted to show a century earlier. Napoleon summoned up this work, read it from cover to cover. Napoleon himself, he wasn't just a tyrant general. The guy read everything he could in physics and engineering, two major branches of study that help you win wars. He also calls in Laplace and said, "Sir, you make no mention of a designer of this system." That's direct reference to Isaac Newton's crediting the hand of God for fixing things. Laplace, in reply, said, "Sir, I had no need for that hypothesis." So there's a lesson in there. The lesson is we're always surrounded by ignorance on some level or another. If you're going to assign God to that ignorance and you lose your curiosity to investigate it, solutions elude you. Isaac Newton said God did it and stopped working on the problem. Laplace, whatever he thought of God, what is certain is that he saw it as a really cool problem that needed a solution. And so, as we go forward, I look at the problems that existed in the past that got solved. I look at the problems that surround us today on the frontier of the advance of science. I imagine we'll solve most of those. Some maybe we're not smart enough as a species to get there. And then, of course, there are the problems yet to be identified because they only show up after we've learned that much more about the universe to even ask such questions. That's what excites me about the entire moving frontier of science.